Today we're going to go over section 2.2, properties of determinants. So to start off, let's find the determinant of this matrix. Remember that if I put straight lines here, or if you see it in the book, that means we're taking the determinant. So how I'm going to find the determinant is I'm going to go along this second row because this row has a 0, which will make the process of finding the determinant easier. So this is equal to, remember that we cross out this row and this column. We say this is 0 times the minor matrix times -1 to the 2 plus 1, 2, 3, 3, 8. We don't even really have to write all this out because this whole term here is going to be equal to 0 because of this 0 here. Okay. Then we're going to put plus 1. I'm going with this entry here, so I cross out the row and the column. It's -1 to the 2 plus 2 times the determinant of the matrix 1, 3, 2, 8 plus 4 times -1 to the 2 plus 3. Cross out this row and this column. And then we find the determinant of 1, 2, 2, 3. By now you should notice a pattern that every other term gets a negative. So here you can see this would have been a negative entry, a negative part of this formula. And then here we're going to have a positive, and this one's going to be negative. So we're left with 1 times 8 minus 6 minus 4 times 3 minus 4. I'm taking the determinant of these matrices. So we get 2 minus 4 times -1, which is 2 plus 4, which is 6. Okay, let's move on. How about this matrix? Let's see if we can find the determinant of this one. Remember that if we have a upper, a lower triangular matrix or a diagonal matrix, and the determinant is just the product of the diagonal entries, this is an upper triangular matrix. You can see you have zeros below this diagonal. So the determinant is just 1 times 3 times -2, which happens to be -6. All right, let's talk about elementary matrices. Remember that a type 2 elementary matrix is when we take the identity matrix and we multiply one of the rows by a non-zero number. So anything in the real numbers except for 0. What's the determinant of a type 2 elementary matrix? Let's start with this 3 by 3 example. Remember, if it's a type 2, then it's a diagonal matrix. So the determinant is just the product of the diagonal entries. So the determinant is always going to be that constant that you're multiplying one of those rows by, this non-zero constant. Now what if we have a type 2 elementary matrix of size n by n? The one I just gave you, the example was a 3 by 3 example, but you can generalize this to any size matrix as long as it's square. The determinant of such a matrix, so the determinant of E, where E is n by n, and a type 2 matrix, and alpha is a non-zero scalar, such that we multiplied 1, exactly 1, no more, no less, one row by alpha, then the determinant is going to be alpha. Just think about it. You got a big matrix. We have the identity matrix, and we just multiply one of those rows by alpha. So the only thing that's going to change is one of those rows where you have a 1 is going to become alpha. It's going to be a diagonal matrix, so the determinant is still going to be alpha. Okay, what about the determinant of a type 3 elementary matrix? Like this one here. Here's just an example of a 3 by 3 matrix. And what I've done is I've multiplied this row, row 2, by a real number, and I added it to row 1. So alpha times row 2, and I added it to row 1. So this is a type 3 elementary matrix. So what is its determinant? Well, notice that a type 3 elementary matrix is either going to be upper triangular or lower triangular. This one happens to be upper triangular. Since it's upper triangular, then the determinant is just the product of the diagonal entries, which is 1. So what if we have a type 3 elementary matrix of size n by n? What is its determinant? So if E is a type 3 elementary matrix, and what we've done is we've multiplied one of the rows, it doesn't matter what row you choose, and then you add it to another row, well, it's either going to be upper or lower triangular. And that's going to tell us that the determinant of E is just the product of the diagonal entries. You're not changing the diagonal entries, so the product of those entries is just 1. And this is for any size type 3 elementary matrix. Now let's do one that's a little bit tougher. We're going to talk about the type 1 elementary matrix. Let's actually just find the determinant of this one. This should be really easy. Notice that this is a type 1 elementary matrix because I switched row 2 with row 3. So I'm going to go along this row. The determinant is 1 times negative 1 raised to the 1 plus 1, and then the determinant of this smaller matrix, right? This one here. And then if I go along this row, I'm going to get plus 0 and another 0. So this is actually the determinant. So if we cancel this out, this is negative 1 to the 2, which just becomes 1. So this is 1 times 0 minus 1. We get negative 1. So the determinant of this particular type 1 elementary matrix is negative 1. And it turns out that any type 1 elementary matrix, its determinant is also negative 1. So what if we have a type 1 elementary matrix of size n by n? Well, if E is such a matrix, so it's a type 1 elementary matrix. I don't like how I abbreviated E here, so let me kind of write this a little bit out. Elementary matrix. Then the determinant of E is negative 1. Now I'm not going to prove that. Maybe you can prove it. I think the book proves it for you, but we can look at a couple of examples. Let's look at a 4x4 example and show you that it's true. So, a 4x4 example. This is the 4x4 identity matrix. Switch any two rows. So how about we switch this one with this one? So we get 0, 0, 1, 0, then 1, 0, 0, 0. And let's say we take the determinant. This is an elementary matrix of type 1. It's going to be very similar. What we need to do is we need to pick a row or a column. I'm going to go with, let's say, this row. this column. So I'll get 1 times -1 to the, this is 3 plus 1, cross this out. And then my matrix is 0, 1, 0, 1, 0, 0, 0, 0, 1. And you notice that this will be just 1. So this is equal to the determinant of this matrix, 0, 1, 0, 1, 0, 0, 0, 0, 1. And notice if I take the determinant, if I go along this row, I'll get 1 times -1 to the 3 plus 1. And then I cross this stuff out and I get that matrix again, which we know is the determinant of this matrix is -1. And this becomes 1. So this ends up equaling -1. So other matrices are similar, like type 1 elementary matrices. If you switch a couple of rows, you'll get something very similar. And it'll always turn out to, the determinant will always turn out to be -1. Now let's look at something interesting. If we have an n by n matrix, any n by n matrix, and we multiply that n by n matrix by an elementary matrix, then the determinant of that elementary matrix with the matrix A is going to be equal to the determinant of the elementary matrix times the determinant of the matrix A. So the full proof is given in the book, but we'll give a proof of when the elementary matrix is a type 2. So suppose E is a type 2 elementary matrix. Well, we want to show that the determinant of E times A is equal to the determinant of E times the determinant of A. Now, since E is a type 2 elementary matrix, we know that we've multiplied one of those rows in the identity, the n by n identity matrix, by some non-zero scalar, let's say alpha. So we can say that this determinant is equal to alpha, and we get alpha times the determinant of A. So what we need to show is that this left-hand side is equal to alpha times the determinant of A. So let's see if we can calculate this piece. So if I have some n by n matrix, just going to write some stuff out. And I multiply it by this matrix E. Let's call this one A. What's going to happen? Well, I'm going to choose one of these rows and I'm going to multiply it by alpha. So let's say it's the second row. It doesn't matter. You're going to take the kth row and you're going to multiply everything in that row by alpha. And what we're going to do is we're going to take the determinant of this matrix going along the row that we multiplied by alpha. So that's what E does. So the determinant of E times alpha A is equal to, well, remember that we're going along the kth row. We're assuming that alpha is along the kth row of this elementary matrix. So you have this elementary matrix here. And because it's n by n, I don't know specifically which row alpha's on. So I'm going to say that it's on the kth row. And what I'm going to do is I'm going to take the determinant. So this is going to be let me make a little insertion here. I'm multiplying everything on this row by alpha, and now I'm going to take the determinant of this matrix E times A by going along this row. So what you're going to get is alpha times AK1. Actually, let me write this out a little bit. -1 to the K plus 1, and then we have this minor matrix. We take the determinant of the minor matrix, MK1, plus, then we have alpha times AK2, -1 to the K plus 2, determinant of the minor matrix, MK2, and so on. You're just going along this row. So this goes all the way to alpha AKN, -1 K plus N, determinant of this minor matrix. We can write this as a summation. So let me write it in a form that's a little easier to handle. This is the same thing as the sum, J going from 1 to N, alpha AKJ, K plus J, MKJ. So this is the one that was changing because we had K1, K plus 1, K1, and then K2 all the way to N. So this is just the nice way to write this determinant. And notice, because this is a summation and this is a scalar, we can take that scalar outside. And so we get alpha times the sum, J is 1 to N, of AKJ, -1 K plus J, determinant of MKJ. But this right here is the determinant of the original matrix, A. So what we get is this is equal to alpha times the determinant of A. So what we've shown is that this determinant is equal to alpha times the determinant of A, which we said was the determinant of E times the determinant of A. So here we've proven that at least for a type 2 elementary matrix, the determinant of E times A is equal to the determinant of E times the determinant of A. And if you're interested in how they proved for the type 1 case or the type 3 case, that's in your book. Okay, let's move on. Something to also notice is that for every elementary matrix we saw, type 1, type 2, type 3, the determinant was non-zero. So you might want to write that down somewhere. So the determinant of E is non-zero for E being an elementary matrix. Remember, determinant of a type 1 was -1. The determinant of a type 2 was equal to alpha, which was a non-zero scalar, and the determinant of a type 3 was equal to 1. So here we have a really nice statement. It says, suppose that A is a matrix that's row equivalent to the identity matrix. Then the determinant of A is equal to the determinant. Well, if it's row equivalent to the identity matrix, we have a bunch of elementary matrices that we can multiply the identity by to get A. But notice that this can be considered another matrix. We can call this B. So this is the determinant of an elementary matrix times B, which, using the last rule we just saw, we can take that elementary matrix out, and then we get the determinant of this B here, but this B is EK minus 1 all the way to E2, E1 times the identity. But we can repeat this process. We can pull off these elementary matrices. So continuing that, we get that the determinant of A is equal to the determinant of EK minus 1 times the determinant, of EK, and then EK minus 1, and so on. But what is the determinant of the identity matrix? Well, its determinant is just 1. So this piece is equal to 1, and we see that the determinant of the matrix A is just the determinant of all of these elementary matrices. Now, why is that important? Well, remember that these determinants are non-zero, every single one of them if they're an elementary matrix. So we get that if A is row equivalent to the identity matrix, this implies that the determinant of A is non-zero. And remember that a matrix is row equivalent to the identity matrix if and only if it's non-singular, meaning it's invertible. So something else we can say is if A is row equivalent to the identity matrix, that means if A is invertible, then the determinant of A is not equal to 0. In fact, this is an if and only if statement. A is invertible if and only if the determinant of A is non-zero.